What if the Big Bang wasn't the beginning but a rebirth? What if our entire 93 billion light-year observable universe is just a single object inside a much larger, older cosmos? This isn't science fiction, it's a possibility being explored by theoretical physicists, challenging our most fundamental understanding of existence. The clues might be hidden in plain sight, in the behavior of black holes and the baffling arrangement of the most distant galaxies spotted by the James Webb Space Telescope. Let's explore this mind-bending possibility together. The standard Big Bang model. So, how did we arrive at our current picture of the universe? The story most of us know is the standard model of cosmology, first mathematically conceptualized by the Belgian priest and physicist Georges Lemaitre in 1927. It states that our universe exploded into being 13.8 billion years ago from a point of extreme density. From this intensely hot state, space itself began to expand. Over billions of years, gravity sculpted this expanding cosmos, pulling matter together to form the vast web-like structure of galaxies we observe today. This model is incredibly successful. It explains the faint afterglow of the Big Bang, the cosmic microwave background, and it accounts for the accelerating expansion of the universe. This acceleration, confirmed in 1998, is often attributed to dark energy, which makes up about 68% of the universe. When combined with dark matter, at around 27%, it appears 95% of our cosmos is made of stuff we can't see or understand. This means that all the stars, planets, and galaxies we can observe make up a mere 5% of reality. The singularity itself represents a point where our laws of physics break down, which is deeply unsatisfying for physicists. The model also struggles to explain why the universe appears so uniform in temperature over vast distances, a puzzle known as the horizon problem. Furthermore, the geometry of space is remarkably flat, an initial condition that seems incredibly fine-tuned and lacks a complete explanation. The black hole universe theory. What if there's a more elegant explanation, one that doesn't require inventing new particles or mysterious forces? A radical alternative, championed by physicist Nikodem Poplawski, proposes that our universe was born inside a black hole within a much larger parent universe. This idea flips our perspective on cosmic origins entirely. Instead of a singularity appearing from nothing, the theory suggests a physical process, the gravitational collapse of matter in a parent universe. Think of it like a star many times the mass of our sun collapsing to form a black hole, but on a cosmic scale. In this model, what we perceive as the Big Bang was actually the moment our universe formed inside that parent black hole. This framework elegantly resolves the issue of what came before the Big Bang, as the parent universe provides a clear preceding state. This cyclical model redefines our cosmic address, demoting our entire universe from everything that is to just one bubble in a potentially infinite cosmic foam. It also provides a physical source for the energy and matter in our universe, sourcing it directly from a pre-existing parent cosmos. In essence, the matter that makes up you, me, and the stars didn't appear from nothing, but was recycled from a previous cosmic iteration. Quantum mechanics and degeneracy pressure. Here's where things get really interesting, and it hinges on a core principle of quantum mechanics. Have you ever wondered what stops a dead star from collapsing forever? The answer lies in a rule established by the brilliant Austrian physicist Wolfgang Pauli. His exclusion principle states that identical particles like electrons cannot occupy the exact same quantum state at the same time. When gravity tries to crush matter into an incredibly small space, this principle creates a powerful outward push known as degeneracy pressure. The more you squeeze, the harder the particles push back. This is the force that supports white dwarfs against collapse, where matter is packed to a density of over 1 million kilograms per cubic centimeter. In even more extreme objects like neutron stars, the pressure is even greater, holding up against densities of over 100 trillion kilograms per cubic centimeter. This pressure is fundamentally different from thermal pressure, which supports a star like our Sun, as it doesn't depend on temperature at all. The strength of this pressure is truly staggering. It's the only known force capable of halting the complete gravitational collapse of a star's core. While we observe it in stellar remnants, applying it to a collapsing universe is a theoretical leap, but one grounded in established quantum principles. The crucial assumption is that these quantum rules hold true even at the unimaginable energies and densities of a universal collapse, providing a physical barrier against infinity. The bounce mechanism. So, if a universe collapses, what happens when this quantum pressure kicks in? Instead of crushing down to an infinite point, a singularity where physics breaks down, the collapse could halt and rebound. This is the Big Bounce, a concept heavily explored in loop quantum cosmology by physicists like Martin Bojewald. In this scenario, as the matter of a parent universe collapses, it approaches the theoretical maximum density allowed by physics, known as the Planck density, which is about 5.1 times 10 to the 96th kilograms per cubic meter. At this point, quantum gravity effects become so powerful they overwhelm everything else. This force stops the collapse in its tracks and triggers a massive, explosive rebound. This rebound event would be incredibly brief but unfathomably violent, essentially resetting the cosmic clock for the new universe. To any observer inside this newly expanding region, that rebound would look and feel exactly like a Big Bang, while potentially preserving information from the prior cosmic cycle. This bounce also offers a potential solution to the black hole information loss paradox, a major conflict between general relativity and quantum mechanics. The paradox questions what happens to the information about matter that falls into a black hole if the black hole evaporates. A bounce mechanism suggests this information isn't destroyed but is instead carried through the rebound event into the new universe, preserving the fundamental laws of physics. Evidence from early galaxies. This might all sound like fascinating speculation, but where's the evidence? It might be hiding in the deepest images of our universe, captured by the James Webb Space Telescope. According to the Standard Model, galaxies should build up gradually. Yet, JWST is finding galaxies that are bafflingly massive and mature. For instance, the GLASS JWST Early Release Science Program, involving astronomers like Rohan Naidu, has identified galaxies like GLASS Z12 at a redshift of 12, meaning we see them as they were just 350 million years after the Big Bang. These galaxies are already 1 billion times the mass of our Sun, far larger than our models predicted was possible so early on. Furthermore, these ancient galaxies appear to host supermassive black holes that are millions of times the Sun's mass, a phenomenon that Standard models struggle to explain so soon after the Big Bang. Under the Standard Model, the universe's gas simply wouldn't have had enough time to cool and condense to form such massive structures so quickly. It's like finding a fully grown ancient oak tree in a field that was barren just a week ago. The timeline doesn't add up. These pre-existing black hole seeds would essentially give galaxy formation a massive head start, neatly explaining the presence of these cosmic anomalies. Galaxy rotation mystery. Now for another cosmic puzzle that might point to the same conclusion. In a random and uniform universe, you would expect galaxies to be spinning in all different directions, with a roughly 50-50 split between clockwise and counterclockwise rotations. But that's not what we see. A 2020 study analyzing over 200,000 spiral galaxies, led by computational astronomer Lior Shamir, found a significant imbalance. There appears to be a preferred direction of spin, and alignment across vast stretches of the cosmos. The statistical probability of this asymmetry happening by chance is less than 1 in a billion. This unexpected alignment, observed across a scale of billions of light years, implies that processes during the formation of the universe were not as random as we thought. This large-scale pattern challenges the long-held assumption that the universe is the same in all directions, a principle that underpins virtually all of our cosmological calculations. This isn't a small, localized effect. The pattern of this cosmic spin is coherent across billions of light years. Shamir's analysis shows the distribution of spin directions fits a dipolar pattern, meaning it has a distinct north and south pole just like a spinning magnet or planet. Such a large-scale coherent structure is extremely difficult to generate after the Big Bang and points instead to a fundamental property imprinted on the universe at its very creation. Schwarzschild cosmology. So, this idea of a universe inside a black hole isn't entirely new. It actually falls under a concept known as Schwarzschild cosmology. The name comes from Carl Schwarzschild, who, way back in 1916, found the first exact solution to Einstein's field equations describing the space-time around a spherical mass, what we now call a black hole. The model suggests that the observable universe is the interior of a black hole existing within a larger parent universe. From our perspective, the Big Bang was the formation of this black hole. From the outside, our entire cosmos would just look like a regular black hole. The size of this black hole's event horizon is defined by the Schwarzschild radius, and for a universe with the mass of ours, this radius is remarkably close to the radius of our observable universe. Mathematically, the singularity at the beginning of our universe is similar to the singularity at the center of a Schwarzschild black hole. The edge of our observable universe, a sphere with a diameter of 93 billion light-years, acts much like a black hole's event horizon, a boundary from which light cannot escape to an outside observer. From the outside, in the parent universe, our cosmic time would appear to be frozen at the event horizon, a classic effect of gravitational time dilation. Conversely, from our perspective inside, time flows normally, and it's the parent universe that is inaccessible to us. This fascinating duality means that our vast, dynamic cosmos could appear as a static, timeless object to any potential observer in the universe that spawned it. Black holes as universe creators. Let's take this idea to its logical conclusion. If our universe was born inside a black hole, what does that imply about the estimated 100 million stellar mass black holes in our own galaxy? It suggests that each and every one could be a gateway, a seed for a new baby universe. This paints a picture of a vast cosmic ecosystem, a multiverse where universes are constantly being born. This concept, known as cosmic natural selection and explored by physicist Lee Smolin, could even offer an explanation for the fine-tuning problem, the mystery of why the fundamental constants of physics are so perfectly set for life. If universes are constantly being created, then perhaps only those whose physical laws allow for the creation of stable black holes can themselves reproduce, leading to a multiverse dominated by life-friendly universes. This theory proposes that our universe is so adept at creating black holes precisely because it was born from one, continuing an unending cosmic lineage. Smolin's theory suggests that the physical constants, like the strength of gravity or the mass of an electron, could slightly mutate with each new universe born from a bounce. Universes with constants that are better at producing black holes will have more offspring, and over countless generations these properties will become dominant. This makes the fine-tuning of our universe for life not a lucky accident but a predictable outcome of cosmic evolution on an unimaginable scale. Torsion and space-time twisting. For a universe to bounce instead of collapsing into a singularity, you need a powerful repulsive force at extreme densities. One candidate for this force comes from an extension of general relativity known as Einstein-Cartan theory. The mathematics behind this were developed in the 1920s by the brilliant French mathematician Élie Cartan. This theory incorporates a property of spacetime called torsion, which accounts for the intrinsic spin of fundamental particles. This spin is a fundamental quantum property like mass or charge that gives particles an inherent angular momentum. In standard general relativity, spacetime can bend but it cannot twist, making the inclusion of torsion a significant modification needed for this theory to work. According to physicists like Nikodem Poplawski, at the densities found inside a black hole, the interaction between torsion and the spin of particles would create a powerful repulsive force. This torsion-induced bounce would be the mechanism that creates a new universe inside every black hole, making them not just cosmic destroyers, but creators. In Einstein's general relativity, gravity is described as the curvature of spacetime, like a heavy ball on a rubber sheet. Torsion adds another geometric property, a twist or spin to the fabric of spacetime itself, which only becomes significant at extreme densities. This twisting effect would act as a repulsive force, preventing matter from collapsing into an infinitely small point, and instead causing it to rebound outwards with tremendous force. Cosmic anisotropy. The evidence for a preferred direction in galaxy spins points to a concept called cosmic anisotropy, the idea that the universe is not the same in all directions. This directly challenges the cosmological principle, a foundational assumption in modern cosmology. This isn't just about galaxy spins. Anomalies in the cosmic microwave background radiation, first noted in data from the WMAP satellite and later confirmed by the Planck satellite, also suggest a large-scale alignment. Physicist João Magueijo famously dubbed this the axis of evil because it aligned with our solar system's plane, a result so strange it had to be a mistake, except it kept showing up with a statistical probability of being random at less than 0.1%. These anomalies, once dismissed as statistical flukes or errors in measurement, are now forcing a re-evaluation of fundamental assumptions, which is exactly how science progresses. The cosmological principle of isotropy has been a cornerstone of cosmology for nearly a century, so challenging it is met with significant scientific skepticism. However, as observational data from projects like the Sloan Digital Sky Survey and the Planck satellite becomes more precise, these persistent anomalies are becoming harder to ignore. If the universe truly does have a preferred direction, it would force us to rewrite our most basic models, and would strongly imply an origin story that involves rotation, just as the black hole universe theory predicts. From the impossible galaxies seen by JWST to the mysterious alignment of galactic spins, we are faced with observations that don't quite fit our standard story of the cosmos. The idea that our universe is inside a black hole, born from a cosmic bounce, offers a potential framework to explain these anomalies without inventing new physics. It suggests we might be part of an endless cycle of creation. What do you think? Are we living inside a black hole? Let me know your thoughts in the comments below. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching InnoVision Tech. A cosmic object 100 times bigger than anything we've ever tracked just entered our solar system, and it looks like it's hunting a smaller, equally strange visitor that arrived just weeks before. On September 12, 2025, astronomers witnessed an impossibility. Two massive, anomalous bodies arriving from opposite ends of the galaxy, set to rendezvous near the Sun. The odds are non-existent, and the evidence points not to a comet, but to a fortress. Let's explore this together. Swan's dramatic arrival. What does it look like when the impossible streaks across the sky? On September 12, 2025, we found out. The SWAN instrument, a solar wind anisotropy sensor aboard the SOHO spacecraft, flagged a new object blazing a path through the inner solar system. The first data sets, analyzed by teams led by SOHO project scientist Bernhard Fleck, were staggering. The object possessed a tail stretching nearly 2.5 degrees across the sky, about 5 times the width of a full moon. To put that in perspective, a tail of that magnitude suggests a hydrogen outgassing rate hundreds of times greater than a typical long-period comet. Its initial brightness was clocked at magnitude 7.4, luminous enough to be seen with backyard telescopes from a distance of over 150 million kilometers. This wasn't some faint smudge, this was a spectacle. News ignited across astronomy networks, and just 2 days later an amateur observer captured a jaw-dropping image showing a streak so immense it barely fit the camera's frame. It was too big, too bright, and its trajectory was already looking far too precise. The raw energy output required to generate such a visible display at that distance was the first red flag that this was something entirely new. Official recognition and growing mystery. How do you classify something that breaks all the rules? By September 13th, the Minor Planet Center, where figures like the late, great Gareth V. Williams once vetted such discoveries, made it official. The object was designated C/2025 R2 or SWAN, acknowledging the instrument that found it. That official stamp kicked off a global frenzy. Its initial orbital eccentricity was calculated at over 0.999, confirming it as a long-period visitor on a path that would take millennia to repeat. The sheer size and luminosity created a wave of disbelief. Veteran astronomers had to reach back to the legendary comet Hale-Bopp of 1997, a comet with a nucleus estimated at 60 kilometers in diameter, to find a worthy comparison. SWAN, however, was already outshining Hale-Bopp at a similar distance from the Sun. It was slicing through the constellation Virgo, growing brighter as it approached its perihelion of roughly 1.0 astronomical units, the same distance as Earth is from the Sun. The question shifted from what it was, to why it had arrived right now with such perfect timing. The numbers didn't just suggest a large object, they hinted at an impossibly active one. The cosmic coincidence. Some things are so unlikely they stop looking like a coincidence. C/2025 R2 SWAN is not the only strange visitor this October. Days before, another object, 3I/Atlas, was already inbound from a completely different part of the sky. Imagine a celestial map. SWAN's path traces back from Aquarius, while Atlas entered from the direction of Sagittarius. Yet, both are set to reach their closest pass by the Sun within the same 10-day window. For Atlas, that's October 17th at a distance of 1.36 astronomical units. For Swan, it's just 3 days later, around October 20th, at a much closer 1.0 astronomical units. Their perihelion points are separated by only about 50 million kilometers, closer than Mars ever gets to Earth. The geometry is what's truly stunning. Both are on steeply inclined orbits, with Swan's path tilted more than 60 degrees and Atlas nearly 90 degrees to the ecliptic plane. As orbital dynamicist Paul Wiegert would tell you, the statistical probability of this kind of synchronized arrival from such different trajectories is infinitesimally small. It's a corridor in space-time that seems to have been deliberately targeted. This is not random chance, it is a rendezvous. Atlas breaks the rules. So what do you do when an object's very existence kind of violates physics? 3I/Atlas, discovered by the University of Hawaii's Asteroid Terrestrial Impact Last Alert System Survey, which was headed by Larry Deneau, first got attention for its composition. Early spectrographs showed a body dominated by nickel, with almost no iron at all. This, honestly, directly contradicts our knowledge of asteroids, which nearly always feature iron-nickel alloys in, pretty predictable ratios, but the anomalies didn't stop there. Instead of water vapor, Atlas's coma was surprisingly pumping out carbon dioxide with its 4.3 micron spectral line dominating every reading. But the real smoking gun was its movement. Observers logged 3 distinct non-gravitational accelerations, on July 29th, August 14th, and August 30th. These weren't smooth pushes. They were sharp bursts, delivering a delta V of several meters per second each time. The behavior was so precise it was dubbed thrust mix modulation, which, honestly, implies a controlled engine burn that was adjusting its composition output. The data held up across multiple observatories, painting a pretty clear picture. This thing was under its own power and, yeah, on a mission. The physics just honestly left no other room for interpretation. Swan, the fortress. If Atlas is a nimble drone, then Swan is, well, a battleship. The scale of C/2025 R2 is hard to even comprehend, but honestly it's the data that paints a pretty radical picture. One that has driven speculators like Harvard's Avi Loeb to consider similar theories for other objects. It all began with reflectance data. Swan's core has an albedo, or reflectivity, that's far higher than a typical dark comet nucleus, actually matching the signature of polished metal. Some analysts argue it fits a nickel-cobalt blend, which is an alloy used for its immense strength. Then, reports started coming in about a silvery halo around the nucleus, an anomaly some interpret as a plasma envelope or maybe even an electromagnetic shield. This is where it earned the nickname, the Fortress. Unlike Atlas, Swan appears steady and honestly invulnerable, refusing to fragment as it nears the sun. Even its tail shows evidence of microthrusts, tiny rhythmic pulses at a consistent frequency that, frankly, defy natural outgassing. Add in its 22,554-year orbit, and you have an object that appears to be ancient, armored, and well, on a deliberate, powered course. It isn't just passing through, it's arriving. Mission theories. When a 1 in a trillion coincidence happens, you kind of have to consider it wasn't a coincidence at all. The timing, the geometry, and all this anomalous behavior have really fueled mission theories. One is a scheduled refueling run, an idea that actually fits with concepts of advanced astroengineering proposed by physicists like Freeman Dyson. A more unsettling theory is, well, an intervention. A rendezvous to neutralize a malfunctioning unit. The estimated power levels, Atlas at 10 gigawatts and Swan at a staggering 10,000 gigawatts, suggest energy reserves needed for active maneuvering, not just passive drifting. There's also the audit chain scenario that 1I/Oumuamua in 2017 and 2I/Borisov in 2019, both on hyperbolic trajectories, were scouts. Atlas was a more advanced follow-up, and now Swan is the main event. In every case, the sun is the rendezvous point, the most powerful energy source in the system. The evidence really forces us to ask, if this is a mission, what is the objective? These aren't just rocks, they're actors on a cosmic stage. Ancient connections. An orbit of 22,554 years is, a link to a different chapter of human history. The last time Swan would have passed was around 20,000 BCE, right at the peak of the last glacial maximum. This is where the story connects to Göbekli Tepe, a site in Turkey built around 9500 BCE. Researcher Martin Sweatman has proposed a controversial theory that its pillars are an astronomical observatory, recording a cataclysmic comet impact that triggered the Younger Dryas climate shift. He argues that Pillar 43 specifically tracks a long-period celestial object. Mainstream archaeologists, including the site's original lead excavator Klaus Schmidt, have strongly disputed this, maintaining the carvings are symbolic. Still, the timing is, hard to ignore. If Swan is on a recurring path, its last visit coincided with a transformative period for humanity. Whether that is a coincidence or a clue remains a fiercely debated question. It adds a layer of mythic resonance to an unbelievable event, suggesting we may have seen this visitor before. The blackout window. Just when things are about to get interesting, the curtains are being drawn. From October 8th to 18th, every major ground-based observatory from the Very Large Telescope in Chile to the Keck Observatory in Hawaii is effectively blind. This solar conjunction is predictable. What isn't normal is the alleged response. According to inside sources, memos from U.S. Space Command and the ESA have directed teams to suspend all imaging. The official rationale is to protect sensitive optics from the sun's glare. But that doesn't explain why radar facilities like Arecibo's successor, which are immune to solar glare, would also be ordered to stand down. This specific detail makes the official story fall apart. Proposals for alternative observation methods have reportedly been denied, and data requests have been delayed. Several telescope allocation reviewers describe explicit orders to avoid public statements. The result is a forced information vacuum at the most critical moment. Underground resistance. When the official channels go dark, the people build their own. The blackout order may have silenced major observatories, but it ignited a firestorm in the amateur and independent astronomy communities. Veteran tracker Bill Gray put out a call to arms across public forums: keep your scopes on the sky, log everything, and share the raw data on open-source servers. A distributed web of astronomers with powerful 14 and 20-inch telescopes answered. Collectives like the Ibero Tracker Group in Europe began pooling their photometric and astrometric data feeds. Leaks suggest plans to use radio telescopes to pierce the solar glare. This grassroots effort has become the only real-time source for what might happen during the blackout. It's a powerful narrative of decentralized science, a global network ensuring no data disappears. When Swan and Atlas re-emerge, the first images confirming their post-perihelion behavior might come from a garage, not a government lab. This has become a testament to citizen science. Power estimates and implications. Let's talk about the energy required to make these objects move. Atlas's accelerations required a power source of around 10 gigawatts, the output of 10 large nuclear power plants, but that is dwarfed by Swan. Based on its luminosity, its suspected micro-thrusts, and the energy needed for a plasma shield, the Fortress could be wielding something close to 10,000 gigawatts. That is more raw output than the entire power grid of planet Earth combined. On the Kardashev scale, a civilization capable of controlling energy on this level is approaching Type 1 status. These are not trivial anomalies. These figures are the hardest evidence to dismiss as natural phenomena. They move the conversation from astronomy into astroengineering and contact theory. The sheer physics involves screams that we are dealing with a technology far beyond our own, powered by a source we can't yet comprehend. This is the bottom line that makes the engineered object hypothesis so compellingly logical. The facts are as clear as they are unnerving. Two anomalous objects defying all statistical odds have entered our solar system on a synchronized path. One appears to be a powered drone, the other an armored fortress. They are scheduled for a close encounter during a 10-day window where they will be conveniently hidden from our best telescopes by the sun, accompanied by an official top-down order for radio silence. This has forced the search for answers into the hands of a global network of citizen scientists. Are we witnessing a cosmic accident, a pre-planned mission, or something else entirely? Whatever the truth is, we are about to find out. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching InnoVision Tech. A mysterious object is racing toward our solar system at incredible speed, and scientists are scrambling to understand what it really is. In the summer of 2025, astronomers made a discovery that has sent shockwaves through the scientific community. A massive visitor from interstellar space that's unlike anything we've ever encountered. Some researchers are asking the unthinkable question: could this be something artificial? Today we'll explore the mind-bending discovery of 3I Atlas and investigate whether we might be witnessing our first contact with alien technology. A rare visitor from deep space. Picture this. You're looking up at the night sky, completely unaware that something extraordinary is racing toward us from the depths of interstellar space at unimaginable speed. In the summer of 2025, astronomers detected exactly that, a massive cosmic wanderer that has been traveling through the galaxy for potentially billions of years before finally entering our solar system. This isn't just any ordinary asteroid or comet from our familiar cosmic neighborhood. This is 3I Atlas, a visitor from another star system entirely, carrying with it secrets from the far reaches of our galaxy that could revolutionize our understanding of how planetary systems form and evolve. What makes this discovery absolutely mind-blowing is that we're witnessing only the third confirmed interstellar object ever detected in human history. The rarity of such encounters means that most of us will never see another visitor like this in our lifetimes. As 3I Atlas races through our solar system at 61 kilometers per second, it's providing scientists with an unprecedented opportunity to study materials that originated around a completely different star, potentially offering our first glimpse into the composition and characteristics of distant worlds we may never be able to visit directly. The breaking discovery. Here's the moment that changed everything we thought we knew about our cosmic neighborhood. The discovery of 3I Atlas represents only the third confirmed interstellar object ever detected passing through our solar system, placing it in an extraordinarily rare category of cosmic visitors. To put this rarity in perspective, astronomers estimate that only one interstellar object larger than 100 meters crosses our solar system annually. Yet most remain completely undetected due to their incredible speed and darkness. Robert Jedicka from the University of Hawaii has calculated that detecting these objects requires perfect timing and cutting-edge technology working in harmony. The significance of 3I Atlas cannot be overstated. It joins the legendary one, Oumuamua, discovered in 2017, and 2I Borisov found in 2019 as the only confirmed messengers from other star systems. What makes this discovery particularly groundbreaking is its massive size and unusual characteristics that are forcing scientists to reconsider their understanding of interstellar objects. Unlike typical asteroids or comets from our solar system, these visitors carry secrets from distant star systems, potentially harboring materials and information that could revolutionize our understanding of planetary formation, galactic evolution, and perhaps even the possibility of life beyond Earth. Each new interstellar detection brings us closer to understanding the true nature of our galaxy's wandering population. The discovery story. The incredible story of how we discovered this cosmic wanderer began in the final days of June 2025, when the Atlas telescope system at Rio Hurtado Observatory in Chile captured something extraordinary moving against the starfield. Larry Deneau, a key member of the Atlas survey team at the University of Hawaii, was conducting routine observations when the automated detection software flagged an unusual fast-moving object. The initial designation A11PL3Z was assigned to this mysterious visitor as astronomers worldwide scrambled to confirm its interstellar origin. John Tonry, the principal investigator of the Atlas project, immediately coordinated with observatories across the globe to track the object's trajectory and confirm its hyperbolic orbit. Within 48 hours of detection, follow-up observations revealed pre-discovery images dating back to June 14, 2025, indicating the object had been silently approaching our solar system for weeks. The challenge of detecting 3I Atlas stemmed from its path through the dense star fields near Sagittarius, where countless background stars made it nearly invisible against the crowded stellar backdrop. Once confirmed as an interstellar visitor, the Minor Planet Center officially designated it as 3Y Atlas, marking a historic moment in astronomy. This rapid confirmation process demonstrated the remarkable advancement in our ability to detect and track these rare cosmic messengers. A stranger in our midst. Alright, get ready to be amazed by the extraordinary characteristics that make 3I Atlas unlike any object we've ever studied in our solar system. This interstellar giant is racing through space at a mind-boggling 61 kilometers per second relative to our sun, a velocity so extreme it actually proves the object originated from beyond our solar system's gravitational influence. Marco Michelli from the European Space Agency has determined that 3Y Atlas measures approximately 11.2 kilometers in diameter, making it significantly larger than both previous interstellar visitors combined. To put this massive scale in perspective, this cosmic wanderer is roughly the size of a small city, totally dwarfing the mysterious Oumuamua, which measured only about 400 meters in length. Daryl Seligman from Michigan State University pointed out that the object's brightness and size make it an unprecedented target for detailed scientific study. Unlike typical solar system objects that follow predictable elliptical orbits around the Sun, 3I Atlas follows a hyperbolic trajectory that will carry it back into the depths of interstellar space. The comet has developed a spectacular 25,000-kilometer-long tail as solar radiation heats its ancient ices, creating a magnificent display visible through powerful telescopes. This combination of extreme size, speed, and activity makes 3I Atlas a once-in-a-lifetime opportunity for astronomical research. The predecessors. To understand the true significance of 3I Atlas, we really need to look back at the groundbreaking discoveries that paved the way for this moment. The very first interstellar visitor, 1I Oumuamua, was discovered on October 19, 2017 by Robert Warwick using the Pan-STARRS 1 telescope in Hawaii. This cigar-shaped object, measuring roughly 400 meters long, totally baffled scientists with its unusual tumbling motion and mysterious acceleration that couldn't be explained by gravitational forces alone. Avi Loeb from Harvard University famously proposed that Oumuamua might be artificial in origin, sparking some pretty intense debate in the scientific community. 2 years later, amateur astronomer Gennady Borisov discovered 2Y Borisov on August 30, 2019 from his observatory in Crimea. Unlike the enigmatic Oumuamua, Borisov behaved like a typical comet, developing a coma and tail as it approached the Sun. Alan Fitzsimmons from Queen's University Belfast led extensive spectroscopic studies that revealed Borisov's composition was remarkably similar to comets in our own solar system. These discoveries established that interstellar objects come in different varieties, some mysterious and unusual like Oumuamua, others more familiar like Borisov. The cosmic journey. So let's follow the incredible path this ancient wanderer will take as it sweeps through our solar system over the coming months. Davide Farnocchia from NASA's Jet Propulsion Laboratory has precisely calculated that 3Y Atlas will reach its closest approach to the Sun, called perihelion, on October 29, 2025 at exactly 11:41 Universal Time. At this critical moment, the comet will be positioned 1.36 astronomical units from the Sun, about 203 million kilometers away, perfectly situated between the orbits of Earth and Mars for optimal observation conditions. This cosmic dance includes several remarkable planetary encounters that provide unique scientific opportunities. On October 3, 2025, the comet will pass just 0.19 astronomical units from Mars, only 28 million kilometers away, potentially allowing Mars-based instruments to conduct unprecedented close-range observations. Following its solar encounter, 3Y Atlas will swing past Venus on November 3, 2025 at a distance of 0.65 astronomical units before beginning its journey back to interstellar space. Earth remains completely safe throughout this celestial ballet, with the closest approach occurring on December 19, 2025 at a comfortable distance of 1.8 astronomical units, or about 270 million kilometers. This trajectory provides astronomers with multiple observation windows and vantage points throughout the solar system, maximizing scientific opportunities. A scientific goldmine. The arrival of 3I Atlas represents, honestly, an unprecedented scientific opportunity that has mobilized the global astronomical community like never before. Karen Meach from the University of Hawaii is leading an international consortium of researchers conducting comprehensive studies of the comet's composition, structure, and behavior. The James Webb Space Telescope, under observations coordinated by Stephanie Milam from NASA Goddard Space Flight Center, has been scheduled to conduct detailed infrared spectroscopy to identify complex organic molecules within the comet's nucleus. Alan Fitzsimmons from Queen's University Belfast has already detected unusual isotopic ratios in the comet's gas emissions using the Gemini Observatory, suggesting formation conditions vastly different from our local environment. Ground-based facilities including the Very Large Telescope in Chile and the Keck Observatory in Hawaii are providing continuous monitoring of brightness changes and spectral evolution. Bin Yang from the European Southern Observatory has identified traces of exotic water vapor with unusual deuterium concentrations, indicating the comet formed in an extremely cold environment around a different type of star. This coordinated global campaign represents the most comprehensive study of an interstellar object ever conducted, with data collection providing insights into star formation processes, planetary system evolution, and the distribution of life-building molecules throughout our galaxy for decades to come. Unanswered questions. Despite intensive observations, 3I Atlas continues to harbor profound mysteries that challenge our understanding of interstellar objects and their origins. Quanji Ye from the University of Maryland has been tracking unexpected brightness variations that just don't match typical cometary behavior, suggesting the object may have an unusual internal structure or composition. The comet's reddish coloration, observed by multiple telescopes worldwide, indicates the presence of organic compounds, but the exact nature of these materials, well, it remains unknown. Matthew Knight from the Naval Research Laboratory has noted that high-resolution Hubble Space Telescope images reveal intricate details in the coma structure that don't conform to standard comet models. One of the most perplexing aspects is the object's estimated age of 7 billion years, older than our entire solar system, which really raises questions about how such ancient materials have remained preserved during eons of cosmic radiation exposure. Tony Farnham from the University of Maryland has documented irregular outgassing patterns that suggest complex subsurface processes we honestly don't fully understand. The Discovery team, led by Daryl Seligman, acknowledges that many fundamental questions remain unanswered. What star system did it originate from? What caused its ejection into interstellar space? And perhaps most intriguingly, could there be more to this object than meets the eye? These mysteries ensure that 3I Atlas will remain a subject of intense scientific scrutiny. The alien question. Here's where the discussion takes a fascinating and honestly controversial turn that has divided the scientific community. Avi Loeb, the Frank B. Baird Jr. Professor of Science at Harvard University and former chair of the Astronomy Department, has gained international attention for suggesting that some interstellar objects might be artificial in origin. Following his controversial proposals about Oumuamua, Loeb has expressed interest in 3Y Atlas, noting that its unusual characteristics warrant careful investigation of all possibilities, including artificial origins. Sarah Seeger from MIT has emphasized the importance of maintaining scientific rigor while remaining open to extraordinary possibilities, stating that we must examine every aspect of these rare visitors. The Galileo project, led by Loeb at Harvard, represents a systematic scientific approach to searching for evidence of extraterrestrial technology in our solar system. However, most mainstream astronomers, including Paul Chodas from NASA's Center for Near-Earth Object Studies, maintain that natural explanations can account for the observed properties of interstellar objects. Robert Warwick, discoverer of Oumuamua, has consistently argued that these objects, while unusual, fall within the expected range of natural cosmic phenomena. The debate really highlights the importance of maintaining scientific skepticism while remaining open to paradigm-shifting discoveries. Dawn of a new era. The discovery of 3I Atlas signals the beginning of a revolutionary era in astronomy, where interstellar objects will become regular subjects of scientific study rather than once-in-a-lifetime discoveries. Mark Norris from the University of Central Lancashire predicts that advancing technology will soon make these detections routine, fundamentally changing how we study galactic dynamics and planetary system formation. The Vera Rubin Observatory, which began full operations in 2025, is expected to revolutionize interstellar object discovery with its ability to scan the entire visible sky every few nights using advanced LSST camera technology. Michelle Bannister from the University of Canterbury estimates that within the next decade, we'll have discovered dozens of these cosmic wanderers, providing statistical samples large enough to understand their origins and distribution throughout the galaxy. Robert Yadika from the University of Hawaii calculates that the improved Atlas survey system, now operating telescopes in Hawaii, Chile, and South Africa, will detect several interstellar objects annually. This technological revolution means that each new discovery will add pieces to the cosmic puzzle of how materials, and potentially life itself, are distributed throughout our galaxy. The age of interstellar archaeology has officially begun, promising to unlock secrets about distant worlds and the formation of our cosmic neighborhood that have remained hidden for billions of years. From its mysterious origins billions of years ago to its spectacular journey through our solar system, 3I Atlas has challenged everything we thought we knew about interstellar visitors. Whether it's a natural cosmic wanderer or something more extraordinary remains to be discovered. As this ancient traveler continues its path back to the stars, it leaves behind more questions than answers, and opens our minds to possibilities we're only beginning to imagine. Like, share and subscribe to InnoVision Tech for more incredible discoveries from the cosmos. A rare visitor from deep space is racing through our solar system at unprecedented speed, and NASA's latest data has left scientists questioning everything they thought they knew about cosmic visitors. 3I Atlas, the third confirmed interstellar object ever detected, exhibits characteristics so unusual that some researchers are considering the unthinkable. Could this ancient wanderer be more than just a natural comet? As we uncover its secrets, the implications for humanity's understanding of our place in the universe become increasingly profound and, honestly, pretty terrifying. The breaking discovery. On July 1, 2025, the NASA-funded Atlas Asteroid Terrestrial Impact Last Alert System Survey Telescope in Rio Hurtado, Chile, first detected an unusual object later confirmed as 3I Atlas. This interstellar comet was initially spotted at a distance of over 4.5 astronomical units from the Sun, activating alarms across the global astronomical community. Its detection marked the third confirmed interstellar object ever observed passing through our solar system, following 1I Oumuamua in 2017 and 2I Borisov in 2019. The initial observations revealed a hyperbolic trajectory with an incredibly high orbital eccentricity of 6.141. The highest ever recorded for any known interstellar visitor. Larry Deneau from the University of Hawaii's Institute for Astronomy immediately recognized that this wasn't an ordinary solar system object, but a rare visitor that had been journeying through space for billions of years. The object's incoming velocity of 58 kilometers per second relative to the Sun marked it as the fastest interstellar object ever detected, surpassing both Oumuamua and Borisov by significant margins. From the outset, astronomers recognized that 3I Atlas was fundamentally different, initiating a worldwide mobilization of observatories dedicated to tracking this cosmic traveler and unraveling its profound mysteries. The discovery story. Between June 25 and June 29, 2025, the Atlas system had been gathering precursor observations that would later prove crucial in understanding 3I Atlas's trajectory and properties. These pre-discovery images, retrieved from survey archives and including work by the Zwicky Transient Facility at Palomar Observatory in California, helped confirm the object's interstellar path. Sam Dean, an amateur astronomer, contributed critical early tracking data, noting that the comet's trajectory through dense star fields near Sagittarius made early detection extremely difficult. The object's path passed through crowded cosmic neighborhoods, where countless background stars created a celestial camouflage, explaining why it had escaped discovery earlier despite being in the inner solar system for weeks. John Tonry, principal investigator of the Atlas project, immediately coordinated with facilities across the globe to confirm the object's characteristics once it was detected. The challenge of identifying 3I Atlas stemmed from its approach through regions where most sky surveys don't venture due to the overwhelming stellar background. This cosmic game of hide-and-seek had been ongoing since June 14, 2025, when the earliest pre-discovery images show the object silently crossing space. The rapid coordination between professional and amateur astronomers from multiple continents underscores the unprecedented global effort invested in monitoring this mysterious visitor. A stranger in our midst. 3I Atlas exhibits characteristics so unusual they continue to baffle the scientific community and challenge our understanding of natural cosmic objects. Traveling at a staggering 61 kilometers per second relative to the Sun, it far exceeds the speeds of its predecessors like Oumuamua and Borisov, making it the fastest interstellar visitor ever recorded. Its brightness is particularly notable, with a distinct coma and tail forming as solar radiation heats its surface, causing ice sublimation that creates spectacular visual displays. David Jewett from the University of California, Los Angeles, noted that the comet's tail and dust emissions provide rare data about materials formed in distant star systems billions of years ago. Perhaps most puzzling is that its trajectory lies almost perfectly within the ecliptic plane, the flat disk where most planets orbit the Sun, an alignment with merely a 0.2% probability of occurring by random chance. This mathematical precision has prompted serious speculation about whether the object's path represents natural celestial mechanics or something far more intentional. The combination of unprecedented speed, unusual brightness, and statistically improbable orbital characteristics raises fundamental questions about whether 3I Atlas is truly a natural object, or represents something far more enigmatic that challenges our basic assumptions about interstellar visitors. The predecessors. So, to really understand the true significance of 3I Atlas, we have to take a look back at the two remarkable interstellar visitors that came before it, each bringing their own, well, unsolved mysteries. The first, 1I, Oumuamua, was discovered in October 2017 by astronomer Robert Warwick at the University of Hawaii. It immediately stunned the scientific community with its elongated cigar-like shape and honestly, its completely unexplained acceleration away from the Sun, all without any visible signs of outgassing. This mysterious acceleration just defied conventional physics and sparked some pretty intense debate about whether the object could be natural or possibly artificial. Then, in August 2019, amateur astronomer Gennady Borisov discovered 2I Borisov from his observatory in Crimea. This one proved to be a more traditional active comet, showing the typical outgassing behavior you'd expect from solar system visitors. The stark differences between these two ancient travelers, one mysterious and possibly artificial, the other conventionally comet-like, have really intrigued astronomers worldwide and, more importantly, set important baselines for comparison. Mark Norris from the University of Central Lancashire has pointed out that 3I Atlas, being the largest and brightest interstellar object yet discovered, gives us unprecedented opportunities to compare and contrast with its predecessors. This growing catalog of interstellar visitors is finally starting to reveal patterns that could unlock secrets about the diversity, origin, and true nature of these cosmic wanderers from distant star systems. The cosmic journey. 3. I-Atlas's trajectory through our solar system, honestly, follows a carefully orchestrated path that gives us optimal opportunities for comprehensive planetary observation. The object will reach perihelion on October 29, 2025, getting close to the Sun at about 1.36 astronomical units, positioned just perfectly between the orbits of Earth and Mars for extended observation. At perihelion, it'll hit maximum speeds of nearly 68 kilometers per second, which really shows off the extreme velocities you get with interstellar travelers. Paul Chodas from NASA's Center for Near-Earth Object Studies has calculated that while the comet poses no threat to Earth, keeping a safe distance of at least 1.8 astronomical units, its path brings it remarkably close to Mars, Venus, and Jupiter during its trip through the solar system. The precision of this trajectory is pretty striking. It allows close approaches to 3 major planets and provides optimal vantage points for studying inner solar system dynamics. Karen Meach from the University of Hawaii emphasizes that this close approach sequence is, honestly, an unprecedented opportunity to see how an interstellar object interacts with different solar environments and planetary gravitational fields. The object will pass just 0.19 astronomical units from Mars on October 3rd, followed by a 0.65 AU approach to Venus on November 3rd, creating a sort of reconnaissance pattern that seems almost deliberately designed for a comprehensive solar system survey, rather than just a random cosmic passage. A scientific goldmine. 3I Atlas, really represents an unprecedented scientific treasure trove for astronomers and planetary scientists who are studying materials from beyond our solar system. With an estimated diameter somewhere between 0.32 and 5.6 kilometers, it's significantly larger than previous interstellar visitors. That means it actually allows for detailed study of its composition, structure, and evolutionary changes as it interacts with solar radiation. The Hubble Space Telescope, operated by teams led by David Jewett at UCLA, has been tracking dust emissions and nuclear activity, revealing ongoing sublimation of ancient ices and continuous dust release from the object's surface. These observations are providing crucial insights into the comet's volatile content and primordial materials, likely preserved for over 7 billion years, predating our entire solar system's formation. Stephanie Malam from NASA Goddard Space Flight Center is coordinating advanced spectroscopic observations using the James Webb Space Telescope to, hopefully, identify complex organic molecules and unusual isotopic signatures that could reveal the object's stellar birthplace. Current analysis has already confirmed the presence of water ice, both as solid grains and vapor, along with hydroxide ions, suggesting a water-rich composition that's typical of objects formed in the outer regions of planetary systems. The ongoing research aims to characterize the complete molecular makeup, including potential carbon monoxide, methane, and complex organic compounds, offering rare glimpses into the chemical building blocks and formation processes of distant star systems. Unanswered questions. Despite intensive global observation campaigns, 3I/Atlas continues to harbor profound mysteries that challenge our fundamental understanding of interstellar objects and their origins. The object's precise nuclear size remains frustratingly uncertain because the surrounding active coma obscures direct measurements of the solid nucleus, which complicates crucial density and mass calculations needed to determine its true composition and internal structure. While spectroscopic analysis has confirmed the presence of water ice and organic compounds, the detection of other expected volatiles like carbon dioxide and carbon monoxide remains elusive, raising questions about the object's formation environment and preservation mechanisms during its multi-billion-year journey through space. Julia de Leon from Spain's Instituto de Astrofísica de Canarias emphasizes that the object's unusual thermal properties and outgassing patterns don't conform to standard cometary models, suggesting either exotic compositions or structural characteristics not found in typical solar system objects. Perhaps most puzzling is the object's remarkable preservation state. How materials billions of years older than our solar system could remain so well preserved and chemically active after eons of exposure to cosmic radiation and interstellar conditions. Some researchers are beginning to debate whether the object represents a completely natural phenomenon or exhibits features that might indicate artificial construction or enhancement, a possibility that would fundamentally challenge our understanding of what's possible in the cosmos. The alien question. The possibility that 3I Atlas represents humanity's first encounter with extraterrestrial technology has, sparked some pretty intense scientific debate and forced researchers to confront some uncomfortable questions about the object's true nature. Avi Loeb, who's Harvard's Frank B. Baird Jr. Professor of Science, has really emerged as the most prominent advocate for seriously investigating artificial origins. He cites the object's statistically improbable trajectory, its unprecedented velocity, and honestly, its unusual structural characteristics as evidence that, warrant extraordinary investigation. Loeb's analysis suggests that the mathematical precision required for 3I Atlas's path, which actually provides optimal reconnaissance opportunities while passing close to multiple planets, exceeds what we'd reasonably expect from random cosmic events. His Galileo project at Harvard has been mobilized to conduct systematic observations using multiple telescopes worldwide, specifically searching for signs of artificial construction or technological signatures. However, mainstream astronomers like Sarah Seeger from MIT and Alan Fitzsimmons from Queen's University Belfast urge extreme caution, emphasizing that extraordinary claims require extraordinary evidence and that natural explanations should be exhausted before considering artificial hypotheses. The scientific community now finds itself balancing healthy skepticism with the recognition that, if 3I Atlas does represent extraterrestrial technology, the implications for humanity's understanding of our place in the universe would be, revolutionary, and potentially terrifying in their scope and consequences. Observing the visitor. Astronomers across the globe have mobilized an unprecedented array of telescopes and instruments to study 3I Atlas as it journeys through our solar system, creating the most comprehensive interstellar object observation campaign in history. Major facilities including the Very Large Telescope in Chile, NASA's Hubble Space Telescope, and the revolutionary James Webb Space Telescope are collaborating to collect multi-wavelength data that could, hopefully, unlock the secrets of this cosmic visitor. Michelle Bannister from the University of Canterbury notes that this coordinated effort involves over 50 professional observatories and, honestly, numerous amateur astronomers contributing observations and analysis. The Southern Astrophysical Research Telescope has been conducting detailed spectroscopic analysis to identify specific molecules and compounds in the object's coma and tail. Ground-based facilities like the Gemini Observatory and Keck Observatory in Hawaii are providing continuous monitoring of brightness changes, rotational periods, and thermal emissions that reveal internal heat distribution patterns. Canada, France, Hawaii telescope observations have captured deep images showing faint cometary activity even at great distances from the Sun. This international collaboration represents a new model for rapid response astronomy, with data-sharing protocols that allow real-time analysis and immediate follow-up observations when unusual phenomena are detected, ensuring that no critical information about this rare interstellar visitor is lost. Dawn of a new era. The detection and intensive study of 3I Atlas heralds the dawn of a revolutionary new era in astronomy, where interstellar objects transform from rare curiosities into, critical scientific targets that could reshape our understanding of galactic evolution and cosmic chemistry. Robert Jedica from the University of Hawaii estimates that technological advances, particularly the upcoming full operation of the Vera Rubin Observatory with its revolutionary LSST camera, promise to dramatically increase detection rates, potentially allowing astronomers to study dozens of interstellar visitors annually within the next decade. This technological revolution will create an unprecedented catalog of interstellar objects, providing statistical samples large enough to offer meaningful insights into galactic dynamics, planetary system formation processes, and the distribution of complex organic molecules across different stellar environments throughout our galaxy. Mark Norris from the University of Central Lancashire predicts that this growing database will reveal patterns in interstellar object populations that could answer fundamental questions about stellar evolution, planetary ejection mechanisms, and the chemical evolution of the Milky Way. As astronomers continue to unravel the mysteries of 3I Atlas and prepare for an influx of future interstellar discoveries, humanity stands at the threshold of a new cosmic perspective, one that will fundamentally transform our understanding of our place in the universe and the evolutionary history of our galactic neighborhood, potentially revealing whether we truly are alone or part of a larger community of cosmic civilizations. As 3I Atlas continues its mysterious journey through our solar system, it carries with it questions that could fundamentally alter humanity's understanding of our cosmic neighborhood. Whether this ancient wanderer represents exotic natural phenomena or, something far more extraordinary, the implications are honestly staggering. The coming months will be crucial as this interstellar visitor approaches its closest encounter with our Sun, potentially revealing secrets that have traveled billions of years to reach us. Keep following InnoVision Tech for the latest updates on this developing cosmic mystery. Like, share, and subscribe.